This evening, the ocean is doing what it has always done, moving, even when it looks still. Some motions are written in quick lines across the surface, and some are so slow you only notice them by what they carry. A wave can cross a basin in days. A tide can turn a coastline like a metronome, and a current can hold a course for years without ever making a sound. The sea is not one motion, but many, stacked like transparent maps. And tonight, we'll follow the evidence gently, one calm detail at a time. Well, hello there, and welcome back. If we haven't met yet, I'm Madeline Rowe, astrophysicist turned private eye, filing the universe into quiet, orderly case notes, one gentle mystery after another. My office is quiet tonight, not empty, just settled, like a harbour after the last boat has tied off. My desk lamp makes a small, steady pool of light, and the edge of that light seems to drift across the floorboards, the way a gyre drifts across an ocean chart. On the desk, a few loose papers have arranged themselves into a shallow curve, as if an invisible current has been nudging them into a soft eddy. A half-open drawer slides in and out by a millimetre when the building breathes, an almost tide, a tiny rise and fall with no shoreline required. Even the steam from my mug lifts, curls and shears away in faint layers, little atmospheric currents doing their own quiet work above the surface of the room. I open the folder slowly, not with drama, but with definitions, because the ocean is easiest to understand when we give each kind of motion its proper name. In the first section, we'll meet waves, patterns that travel, carrying energy across the surface, while the water itself mostly moves in small, looping paths. Waves are the ocean's handwriting. Quick, repeating strokes made by wind, reshaped by depth, and softened into swell that can arrive from storms you'll never see. Then we'll turn to tides, the ocean's metronome, pulled by the moon and the sun, rising and falling with a rhythm that can be predicted, but never looks exactly the same from one coastline to the next. A tide is, in a way, a very long wave, so long you feel it as a change in water level and a slow reversal of flow, rather than a passing crest. And finally, we'll follow currents, the ocean's long walk, persistent directional motion that carries heat, salt, nutrients, and memory from one region to another. Some currents are driven by wind, some by differences in density, and all of them are shaped by the quiet sideways nudge of Earth's rotation. 3 motions, 3 timescales, 1 ocean, always moving. So we'll start where the eye can follow along most easily, at the surface, where waves sketch their clues in light and shadow. And from there, we'll let the case widen naturally until the tide begins to keep time under our feet and the currents begin to draw their longer routes beneath everything we can see. Waves. A wave is a travelling pattern. That's the first important detail, and it's worth letting it settle. A wave is not the same thing as water moving forward. A wave is the pattern of energy moving through water. The surface rises and falls. A crest follows a trough. And if you could tag a single small parcel of water, a little floating bead of seawater, and follow it as a wave passes, you'd see something like a loop. In deep water, that parcel tends to move in a nearly circular orbit, forward and up as the crest approaches, then back and down as the trough passes. It ends up, after the wave has moved on, close to where it began. The wave travelled, the energy travelled, but the water mostly did a dance in place. That's a kind of magic the ocean performs without thinking about it, and it's a kind of magic we can file neatly if we keep the labels simple. Waves have height, they have wavelength, the distance from one crest to the next. They have period, the time between one crest passing a point and the next crest passing that same point. They have speed, how fast the pattern travels. And those quantities are not independent. They talk to each other, they negotiate, they set terms. In deep water, gravity waves have a special habit. Longer waves travel faster than shorter waves. That means the ocean sorts its own handwriting. If a storm writes a mess of waves, short, steep, choppy wind sea mixed with longer undulations, the longer period waves tend to outrun the rest. They travel ahead as swell, arriving at distant shores as smooth, orderly sets. This is why a coastline can look calm and rhythmic, even when the storm that created that swell is far away, somewhere over the horizon, doing its loud work out of sight. The sea carries messages, not in words, but in periods and heights and directions. When you see swell, you're reading weather that happened elsewhere. You're reading a distant wind field, translated into a moving pattern. This is one of the reasons waves are so satisfying to study. They connect cause and effect without needing drama. Wind writes, the ocean edits, the shore receives. And if you sit long enough, the pattern reveals itself. Now, how does wind write on water? It starts small. A flat surface is rare in nature. Even the smoothest sea has microscopic texture. Wind passing over the surface pushes on those tiny irregularities. The pressure differences and the shear, the rubbing force of moving air, encourage the smallest ripples to grow. At very small scales, surface tension matters, and capillary waves can form. Those tiny ripples then provide a better grip for the wind, and gravity takes over for larger waves. The wind's energy transfers into the water, building wave height over time. But it doesn't build without limits. Wave growth depends on how hard the wind blows, how long it blows, and over how much open water it blows. That open distance is called fetch. A long fetch gives wind more room to work, more space to build a developed sea. If wind blows steadily over a long fetch for long enough, the sea state approaches a kind of balance. The wind inputs energy, waves break and dissipate energy, and the overall wave field becomes statistically steady. That's a quiet word, statistically, and it's one of the most calming words in ocean science. Because waves, in the real ocean, are messy. No two crests are identical. The sea surface is a sum of many wave components with different periods, heights, and directions. But when you step back and let go of the need to track each individual crest, you can describe the whole thing with a spectrum. A wave spectrum is a description of how wave energy is distributed across frequencies. It tells you, for example, whether most of the energy is in long period swell, or in shorter wind-driven chop, or in a mix. It turns the sea into a kind of chord, different notes at different strengths. And from that chord, you can pull out meaningful measures. One of the most widely used is significant wave height. Despite the name, it's not about meaning. It's a statistical quantity. Roughly the average height of the highest 1/3 of waves in a sea state. It tends to correspond to what a trained observer would estimate by eye, and it gives engineers, sailors, and scientists a common language. The ocean's handwriting becomes something you can summarize without flattening it into a single number. You can also speak in terms of peak period, the period where the spectrum has its maximum energy, or mean period, or wave direction, or the spread, the degree to which energy is concentrated in one direction or smeared across many. All of this is a way of acknowledging the truth while staying calm. The truth is, the sea surface is complex. The calm is that complexity has structure, and structure can be described. If you've ever watched sets of waves arriving at a beach, groups of larger waves separated by lulls, you've seen another consequence of superposition. Different wave components interfere. Sometimes crests align and build, producing a larger wave. Sometimes a crest meets a trough, and the surface flattens. This interference can create the feeling of sets and pauses. It's not the ocean deciding to be dramatic. It's the natural consequence of many waves adding together. A crowd doesn't need a leader to form patterns. It just needs rules and time. Now, there's a second key distinction that shapes everything about waves: deep water versus shallow water. A wave's behaviour depends strongly on water depth relative to its wavelength. If the depth is greater than about half the wavelength, we call it deep water, and the wave doesn't feel the bottom much. The orbital motion of water particles decays with depth, and by the time you're deep enough, the motion is small. But as a wave approaches shore, the depth becomes a bigger fraction of the wavelength. Eventually, the wave begins to feel the bottom. That interaction changes the wave speed. In shallow water, wave speed depends mostly on depth. Shallower water means slower waves. And when a travelling pattern slows down, something has to give. Energy flux is conserved in a broad sense, so as speed decreases, wave height tends to increase. The wave shoals. It steepens. The wavelength shortens, and the wave becomes more likely to break. Wave breaking is the ocean's way of dissipating energy. When a wave becomes too steep, the crest outruns the base, and gravity pulls it forward. The elegant orbital motion becomes turbulent. Air is entrained. White water forms. Energy that was organised into a travelling pattern becomes disorganised into heat, turbulence and currents. Breaking is not a failure, it's a release. It's the ocean taking a concentrated message and scattering it into the coastal zone. This is where waves become builders. Breaking waves drive nearshore circulation. They set up longshore currents when waves approach the coast at an angle. They create rip currents, narrow jets of water flowing seaward, when water piled up near the beach finds a path back out. They move sediment, shaping bars and troughs, carving and smoothing shorelines. Coasts are not static boundaries. They are negotiated daily by wave energy. Now, because tonight is a calm case file, we don't need to dwell on danger. We can simply note that waves are powerful, and that power is distributed in patterns. And patterns can be understood. It's the understanding that's soothing. Because the ocean, when it feels mysterious, can make the mind tense. And when it feels describable, even in broad strokes, the mind relaxes. Let's talk about how we measure this moving handwriting. Because measurement is one of the quiet triumphs of modern oceanography. If you want to understand waves, you need time series. You need to watch the surface rise and fall. The simplest tools are buoys, floating instruments that record their motion. A wave buoy can measure acceleration in 3 dimensions and infer the sea surface elevation. From that record, you can compute spectra, wave height statistics, and directional information. Some buoys use GPS to track their position precisely, allowing them to reconstruct how they move with waves. Nearshore, pressure sensors on the seabed can record the pressure fluctuations associated with passing waves. Those pressure changes can be converted to surface wave height, with careful attention to how the signal decays with depth. Acoustic Doppler current profilers, ADCPs, can also be used to estimate wave properties by measuring how the water's velocity fluctuates. These are the patient tools. They sit, and they listen, and they record. But the ocean is wide, and one buoy is one point. To see waves over whole basins, we look from above. Satellite altimeters send radar pulses down to the sea and measure the return time and shape. From the way the returned signal spreads, altimeters can estimate significant wave height. Scatterometers and synthetic aperture radar can infer wind and wave patterns by interpreting surface roughness. Optical sensors can also see wave patterns under certain conditions, though clouds complicate things. There are also shore-based systems. High-frequency radar can map surface currents near coasts, and with special processing, it can sometimes provide wave information. Cameras can track wave breaking and surface patterns. Even ships with their motion sensors contribute data, though ship-based measurements are complicated by the ship itself. All of these measurements feed into models. Wave models take wind input and compute the evolution of wave spectra over space and time. They are not perfect, but they are remarkably good at capturing the broad story: where waves are generated, how they propagate as swell, how they decay, how they interact with currents and coasts. A model is another form of filing. It takes the ocean's motion and arranges it into equations and assumptions. The benefit is not that it captures every crest. The benefit is that it gives us a coherent picture, and coherence is restful. There is another type of wave that often sneaks into conversations and confuses things: tsunamis. They are waves, yes, but they are not wind waves. They are usually generated by sudden displacement of water, often due to earthquakes, landslides, or volcanic activity. In the open ocean, tsunami wave heights can be small, sometimes only tens of centimeters, and hard to see. But their wavelengths are enormous, and their periods are long. They behave as shallow water waves even in deep oceans, because the ocean depth is small compared to their wavelength, and this means their speed depends on depth, and in deep water they can travel incredibly fast, hundreds of kilometers per hour. When they approach shore, the same shoaling and slowing processes can cause their heights to increase dramatically. But tonight, we will let tsunamis remain a brief note in the margin. A reminder that wave is a broad category. A reminder that the same physics, gravity, depth, energy, can produce very different outcomes depending on scale and source. If wind waves are handwriting, tsunamis are a stamped message. Not frequent, not casual, but still part of the ocean's language. Now, there are waves that live beneath the surface, internal waves. The ocean is often stratified. Lighter water sits above denser water. Density depends on temperature and salinity. Warm water is lighter than cold. Fresh water is lighter than salty, so the ocean can form layers. At the boundary between these layers, there can be a kind of interface, an invisible surface inside the sea. Internal waves propagate along these density interfaces. They can have large amplitudes, tens of meters, while the surface looks calm. They move slowly compared to surface waves because the restoring force is weaker. It's not air and water, it's 2 layers of water with a small density difference. Internal waves matter because they contribute to mixing. They move energy around, they stir the ocean's interior, and they connect to tides. Because tides, as we will see, can generate internal tides, internal waves at tidal frequencies produced when the barotropic tide flows over rough topography, like ridges and continental slopes. The ocean is full of hidden motion. If you like mysteries, you can spend a lifetime on internal waves. If you like sleep, you can simply enjoy the thought that the ocean has layers of rhythm, like slow music under faster music, all the way down. Now, before we leave waves, there's a phrase that gets used in oceanography that's both technical and strangely poetic: sea state. Sea sea state is the description of the waves at a time and place, their heights, periods, directions, the overall feel. Sailors use it, scientists use it, forecasts describe it. It is the ocean's mood, quantified. And just like mood, sea state is not a single thing. It's a blend. Wind sea plus swell. One storm's handwriting plus another storm's lingering signature. A sea state can be dominated by swell from far away, even if local winds are light. Or it can be chaotic with locally generated chop. Or it can be mixed. And this is where our case file begins to thicken, because waves do not travel alone. They travel on top of currents. They travel through tidal flows. And those background motions can change how waves behave. A current can steepen waves if it opposes their direction of travel. It can lengthen and flatten waves if it goes with them. Currents can refract wave directions, bending wave rays like light through a lens. Waves can also push water. They produce a subtle net drift called Stokes drift, a small forward motion associated with the fact that particle orbits are not perfectly closed in a real, non-linear wave field. That drift matters near the surface. It can contribute to how things float, how oil spreads, how plankton and debris move. Waves also influence currents through momentum and turbulence. Breaking waves inject turbulence into the surface layer. They influence the mixing of heat and gas. They shape the near-surface structure that currents inhabit. So when we talk about surface currents, we are already talking about waves, whether we mention them or not. Tonight, we will mention them. We will give them their proper place. Because the ocean's motion is not a set of separate folders, it's one file with dividers. We've walked through the fast motion. Now we can move to the motion with a clock you can set your watch by. Tides. If waves are handwriting, tides are punctuation. Regular marks, predictable returns. A high tide is not a random event, it's a consequence of gravity. The moon and the sun pull on Earth's oceans, but the pull is not uniform. The key to tides is not gravity itself. It's the gradient, the difference in gravitational pull across Earth. The side of Earth closer to the moon feels a slightly stronger gravitational pull than the centre. The centre feels a slightly stronger pull than the far side. Those differences create a tidal force that stretches Earth, in a sense, along the line connecting Earth and the moon. The ocean responds by forming bulges. One bulge on the side facing the moon, where the moon's pull is strongest. One bulge on the far side, where the moon's pull is weakest relative to Earth's centre, and the Earth-Moon system's rotation contributes to the balance in the rotating frame. If you imagine an ideal Earth completely covered in water of uniform depth, with no continents, no basins, no friction, you can imagine these bulges smoothly following the moon as Earth rotates beneath them. That is the equilibrium tide, a useful starting picture. But the real ocean is not a smooth shell. It has continents that block and channel flow. It has basins with resonant frequencies. It has shallow shelves where friction matters. It has deep basins where waves can propagate. So the real tide is a dynamical tide, a pattern of tidal waves travelling and reflecting, interacting with Earth's rotation and geography. This is where tides become beautiful, because they become maps. The tide is not high everywhere at once. It's a moving system. In many places, tides are semi-diurnal, 2 highs and 2 lows per day. In some places, they are diurnal, 1 high and 1 low per day. In some places, they are mixed, with unequal highs. These patterns come from the geometry of the moon's orbit, the tilt of Earth's rotation axis, and the way the tide-generating potential decomposes into different harmonic constituents. Harmonic constituents are like notes in a tidal chord. The biggest is often M2, the principal lunar semi-diurnal tide, with a period a little over 12 hours. There's S2, the principal solar semi-diurnal, exactly 12 hours. There are diurnal constituents like K1 and O1. There are many others. And tides in any location can be described as a sum of these constituents, each with its own amplitude and phase. This is one of the most restful things tides offer. They are complex, but they are decomposable. They can be predicted. You can fit a harmonic model to tidal observations and forecast tides for years. And the ocean agrees to that forecast remarkably well, because the forces are steady. The moon does not forget to orbit. The sun does not forget to rise. Earth does not forget to rotate. So the tide continues. Now, let's walk from the ideal picture to the real one. In the real ocean, tidal waves propagate as long waves. Their wavelengths are enormous, thousands of kilometers. And Earth's rotation matters. Rotation introduces the Coriolis effect, which deflects motion to the right in the northern hemisphere and to the left in the southern hemisphere. For long waves like tides, Coriolis can cause the wave to rotate around points called amphidromic points, locations where the tidal amplitude is near zero. Around an amphidromic point, the tide rotates like a slow clock hand. The lines of equal tidal phase, the cotidal lines, radiate out and wrap around. In other words, the tide is not a simple rise and fall everywhere. It's a travelling wave system that rotates, and those amphidromic systems depend on basin geometry and resonance. In the North Atlantic, there are amphidromic points that shape how tides appear on surrounding coasts. In the North Sea, in the Gulf of Mexico, in the Pacific, you can find these rotating patterns. If you look at a global tide map, it looks like the ocean is divided into slow whirlpools of timing, not of water moving in circles necessarily, but a phase of when high tide occurs. It's like the ocean is keeping time with rotating hands. Now, tides are not just vertical motion, they come with currents. As the tide rises and falls, water must flow in and out of bays, estuaries, and along coasts. Tidal currents can be strong in narrow channels. They can create mixing and stirring in shallow seas. They can generate fronts where different water masses meet. They can influence sediment transport. They can be harnessed for energy in some places because they are predictable and persistent. Tides also interact with topography in ways that matter far beyond coasts. When tidal flow passes over rough topography, seamounts, ridges, continental slopes, it can generate internal tides. Energy from the barotropic tide, the depth average tide, is converted into internal wave energy. Those internal waves can propagate away and eventually break, contributing to mixing in the ocean interior. And mixing is one of the keys to the ocean's long-term circulation. So tides are not just a shoreline phenomenon, they are a global engine for moving energy into the deep ocean, quietly, relentlessly, on schedule. Now, if you're lying in bed listening, you might not have a mental picture of internal tides, and that's fine. You can imagine them as slow, underwater swells rolling along invisible boundaries, or as a soft stirring spoon moving through a layered drink, not mixing it instantly, but encouraging it. Mixing in the ocean is not a single violent process. It's the sum of many small processes operating over vast areas and long times. Tides contribute, winds contribute, waves contribute. All together, they keep the ocean from settling into perfect stillness. And perfect stillness in a stratified fluid would be a kind of trapped condition, a locked file. The ocean prefers the drawer slightly open, Now, there are some especially dramatic tides in the world. In places where basin geometry resonates with tidal forcing, tides can be amplified. The Bay of Fundy is a classic example. In some locations, tidal ranges can be huge, but we don't need to chase drama. We can note that resonance exists. We can note that the ocean is, in part, a set of basins with natural frequencies. If you push at the right rhythm, the response grows. That's physics. That's also a useful metaphor for sleep. When you breathe slowly and you let your thoughts drift, you are applying a gentle forcing to a system that has its own rhythms. The mind responds, not instantly, but with repetition. Now, tides also have variations, spring and neap tides. When the sun and moon align during new and full moon, their tidal forces add, and tides tend to be stronger, spring tides. When the sun and moon are at right angles, during first and third quarter, their tidal forces partially cancel, and tides tend to be weaker, neap tides. Again, a simple pattern, a monthly rhythm, a reminder that not all days are the same, even with the same coastline. Tides also have longer-term changes due to orbital cycles and sea level changes, and they can be affected by changing coastal geometry, harbour construction, dredging, sea level rise, changing shallow areas, changes in ice shelves, affecting tide propagation in polar regions. But the essential thing remains. Tides are predictable. And in a world where many things feel unpredictable, predictable motion is soothing. It's a reassurance. Now, we have waves and we have tides, we have fast handwriting and slow punctuation. The final piece is the ocean's persistent movement, the currents. And this is where the case file becomes wide, because currents live everywhere, from the surface to the abyss. Currents are the ocean's transport system. They move heat, they move salt, they move nutrients, they move living things. They move floating things. They move memory. The simplest way to categorize currents is by what drives them. Surface currents are largely driven by wind. Deep currents are largely driven by density differences, temperature and salinity, creating what we call the thermohaline circulation. And everywhere, Earth's rotation shapes the flow. Let's start at the surface. Wind blows on the ocean surface, and because of friction, it pushes water. But the water doesn't move exactly in the direction of the wind. Coriolis deflects motion. In the northern hemisphere, water tends to move to the right of the wind direction. In the southern hemisphere, to the left. And with depth, the direction of current rotates, forming what's known as the Ekman spiral. The net transport in the surface layer, the Ekman transport, is 90 degrees to the right of the wind in the northern hemisphere, 90 degrees to the left in the southern hemisphere in the idealized theory. Real oceans are messy, but the concept is powerful. Wind can drive surface water away from a coast. When surface water moves away, deeper water rises to replace it. That's upwelling. Upwelling brings cold, nutrient-rich water to the surface, fueling productive ecosystems. Wind can also drive surface water toward a coast. That can cause downwelling. These processes shape coastlines, climates, fisheries, but they are still, fundamentally, motion driven by wind and shaped by rotation. Now across ocean basins, winds blow in broad patterns. Trade winds blow westward near the equator. Westerlies blow eastward in mid-latitudes. These wind patterns drive large-scale circulation in the ocean surface, forming gyres, large rotating systems of currents. In the northern hemisphere, subtropical gyres rotate clockwise. In the southern hemisphere, counterclockwise. These gyres include familiar currents, the Gulf Stream in the North Atlantic, the Kuroshio in the North Pacific, the Brazil Current, the Agulhas Current. These are western boundary currents, strong, narrow currents on the western side of ocean basins. Why the western side? Because of the variation of the Coriolis parameter with latitude, something called the beta effect. In broad terms, the combination of wind stress curl and Earth's rotation leads to a circulation that must return somewhere, and the physics of vorticity conservation tends to concentrate that return flow on the western boundary. The result is western intensification, a strong current that carries warm water poleward, a swift river of the sea. This has consequences. Western boundary currents transport heat. They influence weather and climate. The Gulf Stream, for example, contributes to relatively mild climates in parts of Western Europe compared to similar latitudes elsewhere, though the full story involves atmospheric circulation as well. Boundary currents also generate eddies, swirling masses of water that pinch off and roam, carrying heat and salt and nutrients. The ocean is not a smooth conveyor belt. It's a field of currents and eddies, constantly interacting. If you look at satellite maps of sea surface height, you can see these eddies as bumps and depressions, because sea surface height is related to pressure, and pressure gradients drive geostrophic currents. Geostrophic balance is another restful concept. In much of the ocean away from the surface and away from strong friction, flow tends to balance pressure gradients against Coriolis. Water flows along lines of constant pressure, along contours of sea surface height, rather than directly from high to low pressure. This is why currents can follow coastlines and contours, why they can form loops and jets. It's not that water wants to go in circles. It's that in a rotating system forces balance in a way that produces sideways motion. Balance, that word again. It's everywhere in fluid dynamics. Balance is the reason the ocean can be moving vigorously and still feel stable. Now, currents are not only horizontal. There are vertical motions, upwelling and downwelling, sinking and rising. But vertical velocities in the open ocean are often small compared to horizontal ones. Still, over long times and large areas, small vertical motions matter a lot. They are how the ocean ventilates, how surface water is transported into the interior, and deep water returns to the surface. Now we come to the deep ocean. The thermohaline circulation is driven by density. In certain regions, surface water becomes dense enough to sink. This can happen when water cools. Colder water is denser. It can also happen when water becomes saltier, which increases density. In the North Atlantic, in regions like the Labrador Sea and the Greenland, Iceland, Norwegian seas, surface waters can cool and, under certain conditions, sink to form deep water. In the Southern Ocean, around Antarctica, dense water forms as well, including Antarctic bottom water. These dense waters sink and spread along the ocean floor. They fill basins. They create deep currents. Over long timescales, these deep waters eventually rise again, through mixing and upwelling, completing a global overturning circulation. This is often described as a conveyor belt, but the real picture is more complex. Multiple pathways, mixing, eddies, interactions with topography. Still, the central idea is coherent. Density differences drive deep flow. Winds and mixing help bring deep water back up. And the whole system transports heat and carbon and nutrients around the globe. This matters for climate. The ocean stores vast amounts of heat. It stores carbon. It acts as a buffer. Changes in overturning circulation can influence regional climates. There is scientific interest in how the overturning might respond to freshwater input from melting ice, changes in winds, changes in stratification. But for tonight, we can hold the idea gently. The ocean's deep circulation is slow, but it is not inert. It is a living motion, a slow breath. Now, remember how we said tides contribute to mixing? This is one of the connections. Deep overturning requires mixing. To lift dense water back upward, you need energy. Tidal energy dissipated through internal waves provides part of that mixing energy. So the moon's pull is not just shaping tides on shore, it is contributing indirectly to the long-term circulation of the deep ocean. Gravity helps stir the sea. Waves also contribute. Breaking waves inject turbulence and mixing in the surface layer. Storms can deepen the mixed layer. Langmuir circulation, wind and wave interactions forming long, parallel vortices, can enhance mixing near the surface. Everything connects, and that connection is what makes a big episode like this satisfying. Now, how do we measure currents? Because currents, like waves, are motion that requires observation. We use drifters, floating instruments designed to follow surface currents. They provide Lagrangian data. They show where water goes. We use floats, like Argo floats, that dive and rise, measuring temperature and salinity, and drifting at depth. They map the interior. We use moorings with current meters and ADCPs that measure velocities. We use satellite altimetry to infer geostrophic currents from sea surface height gradients. We use satellite sea surface temperature and colour to track fronts and eddies. We use HF radar near coasts to map surface currents. We use ship-based measurements. We build models that assimilate these data. We create reanalyses, best estimates of the ocean state over time. Again, filing, taking motion and turning it into a coherent record. There is a detective-like pleasure in this. If you want to know where a water mass came from, you can track its properties, temperature, salinity, oxygen, nutrients, traces. You can infer pathways. You can look at water like evidence, not in a dramatic way, but in a careful way. And that carefulness is a kind of calm. Now let's bring the three motions together, because a case file like this is not complete until the suspects are in the same room. Waves, tides, currents. They interact. They modulate each other. They change the conditions under which each exists. Consider wave-current interaction. If waves propagate into an opposing current, their wavelength shortens and their height can increase. They steepen. This can make breaking more likely, even in deeper water than you'd expect. This is why certain ocean regions with strong currents can have particularly steep, chaotic seas under certain wind conditions. The current is not creating waves, but it is changing their shape. It is changing their energy distribution. It is editing the handwriting. Waves can also affect surface currents. Stokes drift adds a forward motion near the surface. Wave breaking injects turbulence, affecting momentum transfer. Waves can change how wind stress is partitioned. Some wind energy goes into growing waves rather than directly accelerating currents. Wave dissipation returns momentum to the ocean, modifying the surface layer. In intense storms, these wave-related effects can significantly alter surface current estimates compared to models that ignore waves. It's a reminder that the ocean surface is not just water plus wind. It's water plus wind plus a wave field that mediates the interaction. Now consider tide current interaction. Tidal currents can combine with background currents, speeding them up or slowing them down. Tidal mixing can influence stratification, which affects density-driven currents. In shelf seas, tides can create strong mixing that keeps water columns well mixed, influencing temperature distributions and ecosystems. Tidal fronts can form where mixed and stratified waters meet. Those fronts can steer currents and concentrate biological activity. Tides also generate internal waves, which contribute to mixing and thus influence deep circulation. Again, punctuation affects the whole paragraph. Now consider wave-tide interaction. In shallow water, wave breaking depends on depth, and depth changes with tide. At high tide, waves may break closer to shore or with less intensity on a given bar. At low tide, the same swell can break farther out or more steeply or in different patterns. Tides modulate surf. They change nearshore wave energy dissipation. They change currents like rips and longshore flows. So even the fast handwriting of waves is influenced by the slow metronome of tides. And the shoreline, as always, is where these interactions become visible. Now we can take a slow walk through an imagined coastline and let these interactions play out, like a scene in a quiet film. Picture a broad continental shelf. Offshore, the sea is deep. Swell arrives from far away, long period waves marching in steady lines. They travel quickly in deep water. As they reach the shelf break, depth decreases, wave speed decreases, wavelength shortens. The wave rays, paths of energy, begin to bend due to refraction, because parts of the wavefront slow sooner than others. The swell lines adjust, becoming more parallel to the depth contours. This is why waves often approach beaches more directly than their offshore direction might suggest. The ocean aligns itself with the shore. As the waves shoal, their height increases. The sea begins to show more relief. Then, near the surf zone, breaking begins. White water appears. Energy dissipates. Water is pushed shoreward by the momentum flux of breaking waves, creating a setup, an elevated mean water level near shore. That setup drives pressure gradients that contribute to nearshore currents. If the waves approach at an angle, longshore currents flow along the beach. If there are variations in breaking intensity due to sandbars, channels, rip currents can form. All of this is happening on top of the tide. At high tide, the breaking zone shifts. At low tide, it shifts again. And beneath all of it, there may be an along shelf current, driven by winds or larger scale circulation, carrying water steadily along the coast. If you sit and watch long enough, you might feel like the ocean is complicated. If you sit and watch longer, you begin to feel like it's a layered dance. Each layer has rules. Each layer has timescales. And the combination is not chaos, it's orchestration. Now, sometimes the ocean produces waves that feel exceptional. Rogue waves, large, unexpected waves that can exceed what you'd expect from average conditions. They have many contributing mechanisms: constructive interference, focusing by currents, non-linear wave interactions. In a statistical sea state, extremes are expected occasionally. If you have a random process, rare events occur. But some conditions can increase the likelihood. Strong currents opposing waves, complex wave spectra with multiple directions, non-linearities. Rogue waves are a reminder that even in a system with structure, extremes can happen. But tonight, we don't need to fear them. We can simply note that the ocean's statistical nature includes tails. And tails are part of any distribution. It's math, not malice. It's the ocean being a big system. Now, there's another calming way to frame waves, tides, and currents as energy pathways. Wind energy enters at the surface. It becomes waves and currents. Wave energy travels and dissipates, often near shore. Tidal energy enters through gravitational forcing. It becomes tidal currents and internal tides. It dissipates through friction and mixing. Heat energy enters through sunlight and atmosphere-ocean fluxes. It creates density differences. It drives stratification and circulation. The ocean is constantly receiving energy, moving it, transforming it, dissipating it. In other words, the ocean is a machine, not a mechanical machine with gears you can see. A fluid machine, a machine whose components are patterns. This is why it's so satisfying to file, because a pattern is a piece of evidence you can hold without needing to hold it physically. Now, I want to take you back to the office for a moment, because the office is the stage we use to make sense of motion. On my desk, the case folder is open. Inside, 3 maps. One map shows wave rays, lines curving toward shore. Another shows cotidal lines, spiraling around amphidromic points. The third shows currents, arrows sweeping around gyres, thickening into boundary currents, swirling into eddies. If you stack these maps, you begin to see the truth. The ocean is not one map. It is multiple maps laid on top of each other. And if you try to stare at all of them at once, your mind tightens. But if you let your attention glide from one to the next, you can feel the layered calm. Tonight, we can let the mind do what the ocean does: layer, blend, balance. So let's go deeper into each motion, slowly, with a detective's patience and a sleeper's gentleness. We'll return to waves again, because waves are the easiest door into the physics. Consider dispersion again. Longer waves travel faster in deep water. That's why swell becomes more orderly with distance. If a storm generates a range of periods, the long period components outrun the short period ones. The swell arriving at a distant shore often has a narrow band of periods. It can feel like the ocean is breathing in slow, even pulses. This is also why, if you watch the sea during a distant storm, the swell can gradually increase in period as the first arrivals are the longer waves, then shorter ones catch up. The sea's rhythm can change without any local wind change. It's distant information arriving. Now consider wave directionality. Waves do not always come from one direction. A sea state can be multi-directional. Multiple swell systems can intersect. Local wind sea can add a different direction. This can create a cross sea where waves come from different directions, making the surface more complex. From a spectral point of view, energy is distributed not only across frequency, but across direction. Directional spectra are richer descriptions. They matter for understanding how waves impact coasts, how they interact, how they contribute to loads on structures. But for sleep, we can hold the idea gently. The ocean can hum in more than one note at once. Now consider fetch limited growth. If wind blows over limited fetch, waves develop but do not reach the fully developed state of an open ocean storm. Wave height and period depend on fetch and wind speed. There are empirical relationships and theoretical frameworks that describe this. Again, the ocean has growth curves. It doesn't jump instantly from calm to rough. It develops. It responds. It reaches a balance. Then it decays when the forcing stops. Decay is another restful concept. When wind stops, waves do not vanish immediately. They decay as energy is dissipated by breaking, whitecapping, and interactions. The wave spectrum shifts. Energy moves toward longer waves in a sense because shorter waves dissipate more quickly. Swell can persist. The ocean lingers. It doesn't end abruptly. Now we can talk about wave energy in a simple way. Wave energy is related to wave height. In deep water, wave energy per unit area is proportional to the square of wave height. and this means a small increase in wave height can mean a larger increase in energy. And wave power, the rate of energy transport, is related to energy times group velocity. Group velocity is the speed at which wave energy travels. In deep water, group velocity for gravity waves is half the phase velocity. This is another quiet detail that can be satisfying. The crests move at one speed, but the energy envelope, the groups, move at a different speed. This is why you can see wave groups, sets of waves that seem to travel as clusters. The ocean contains patterns within patterns. Now, why do we care about waves beyond beauty? Because waves shape coasts, influence navigation, affect mixing, contribute to air-sea exchange, and are a source of renewable energy. Wave energy converters attempt to capture some of that power, but wave energy is irregular, variable, and requires robust engineering. Understanding wave spectra, extreme conditions, and site-specific behaviour is essential. Again, tonight we don't need to build a device, we just need to understand the motion, but it's nice to know that waves are not only a poetic phenomenon, they are measurable, useful, and consequential. Now, let's shift back to tides with the same patient tone. The dynamical tide is a wave, a very long wave. And like other long waves in a rotating system, tides can be described using equations of motion and continuity, with Coriolis and friction. But we can keep it conceptual. Tidal forcing creates a potential. The ocean responds. Because the ocean is constrained by continents, the response becomes a set of tidal waves. These waves reflect from boundaries, interfere, and form standing or partially standing patterns in basins. Resonance can amplify tides, where the natural period of a basin matches the tidal forcing period. Friction and bottom drag dissipate energy. In shallow areas, friction is stronger. This means tides can lose energy as they propagate over shelves. This energy dissipation contributes to mixing, so tides are both a wave phenomenon and an energy input to the ocean. Now consider the idea of tidal constituents again. Harmonic analysis treats the tide as a sum of sinusoids at known frequencies. By fitting observed tides, you can estimate amplitudes and phases for each constituent. Then you can predict future tides. This works because the astronomical forcing frequencies are known and stable. The ocean response is linear enough in many places to make this a good approximation. Non-linear effects exist, especially in shallow estuaries where tides distort, producing overtides and compound tides. But the core remains. Tides are predictable. Now, there is something quietly delightful about amphidromic points. An amphidromic point is not a hole in the ocean. It's not a location where nothing happens. It's a node in the tidal wave pattern. Around it, the tide rotates. This rotation is a consequence of Earth's rotation and basin geometry. If you draw cotidal lines, you can see the rotation like a clock face. High tide moves around. In some basins, the rotation is counterclockwise in the northern hemisphere, clockwise in the southern, depending on the system. This is the ocean behaving like a rotating fluid. Again, balance. Now, tides also come with tidal currents that can be used to generate internal waves. Internal tides can propagate away from generation sites and contribute to mixing when they break. Mixing is essential to maintain the stratification and overturning balance. So, once more, the moon's pull is connected to the deep ocean's slow motion. It is strange and calming to think that the moon is stirring the sea, not by pushing it directly like a spoon, but by setting up rhythms that convert into internal waves and dissipate. A gravitational whisper becomes a deep ocean stir. Now let's walk into currents with the same attitude. Currents are often described in terms of geostrophic balance. In the open ocean, away from boundaries, currents are largely geostrophic, pressure gradients balanced by Coriolis. This means if the sea surface is higher in one region than another, water tends to flow along contours, not straight downhill. The sea surface height anomalies measured by satellites can thus be used to infer currents. This is why sea surface height maps show eddies. Eddies are rotating features, like atmospheric highs and lows, but in the ocean. A warm core eddy might have a raised sea surface in the centre. A cold core eddy might have a depressed sea surface. These eddies can transport water properties, they can trap water masses, they can influence biology by trapping nutrients or isolating water. They can contribute to mixing and transport. They are part of the ocean's texture. Now, wind-driven currents have the Ekman layer. The Ekman layer is the surface boundary layer where wind stress is transmitted into the ocean through turbulent mixing. The resulting Ekman transport creates convergence and divergence patterns. Where Ekman transport converges, water piles up, creating a higher sea surface. This creates pressure gradients that drive geostrophic currents. This is how wind forcing creates gyres. Wind stress curl leads to Ekman pumping, vertical motion of water. In subtropical gyres, Ekman convergence leads to downwelling, creating a dome of warm water. In subpolar gyres, Ekman divergence leads to upwelling, creating a dome of colder water. This is the ocean's large-scale structure. It's a system of domes and depressions, of convergence and divergence, all linked to wind and rotation. Now, the deep circulation involves water mass formation. In polar and subpolar regions, surface water can become dense and sink. This forms deep water. In the North Atlantic, this contributes to North Atlantic deep water. In the Southern Ocean, Antarctic bottom water forms. These water masses spread along isopycnals, surfaces of constant density. They fill basins. They move slowly. Their pathways are influenced by topography, ridges, basins, sills. Mixing and upwelling bring deep water back toward the surface. This overturning is an essential part of the climate system. The ocean absorbs heat and carbon and redistributes them. Now, to keep it gentle, we can think of currents as the ocean's memory of forcing. Winds change daily, but currents can persist. The ocean integrates wind stress over time. The ocean stores heat. The ocean stores salt. Currents carry these stored quantities. In other words, the ocean is a low-pass filter. Fast fluctuations are smoothed. Slow changes matter. This is why the ocean can feel steady even when the atmosphere is chaotic. The ocean's inertia is calming. It doesn't react instantly. It responds with patience. Now, let's connect currents back to waves and tides in more detail. Wave-current interaction is not just about steepening. It also affects wave propagation direction. If a current varies in space, waves moving through it experience refraction. Wave rays bend toward regions of slower group velocity. If the current is opposing, group velocity relative to the ground decreases and waves can focus, increasing wave height. If a current is following, waves can spread. This is similar to light refraction, but with currents as the refractive medium. It's a quiet analogy. Now, waves influence currents through Stokes' drift and wave-induced stresses. In the surface layer, the Lagrangian mean flow includes Stokes' drift. This can affect transport of floating material. It can contribute to Langmuir circulation, where wind and wave interactions produce parallel streaks on the sea surface, with convergent zones where foam and debris accumulate. If you've ever seen long streaks of seaweed or foam aligned with the wind, you've seen Langmuir circulation at work. It's the ocean organising surface material into lines, a subtle pattern. Now, tides influence currents through tidal currents, which can modulate stratification and mixing. Tidal mixing can reduce stratification in some regions, allowing deeper nutrients to reach the surface. In shelf seas, tidal mixing can maintain well-mixed water columns. In deeper oceans, internal tides contribute to mixing in the interior. This can influence the distribution of water masses and the overturning circulation. So tides connect to currents through mixing and energy pathways. Now, there is a phrase oceanographers sometimes use, the oceanic energy budget. Winds input energy. Tides input energy. That energy must be dissipated. Dissipation occurs through turbulence, friction, mixing. The ocean's motion is sustained by energy input and balanced by dissipation. In a steady state, inputs equal outputs. In a changing climate, the balance can shift. Storm patterns can change wave climates. Sea level rise can change tidal propagation and dissipation. Stratification changes can influence internal wave propagation and mixing. Currents can shift. But the essential framework remains. The ocean is an energy system. Now, let's drift into a gentle, detailed journey through the ocean's 3 clocks. We'll start at the smallest timescale, but not too small. Imagine a light breeze over a calm sea. Small ripples appear. Capillary waves shimmer. They are tiny, and surface tension matters. They act as a texture. Then the breeze strengthens. Short gravity waves appear, a little chop. The surface becomes rougher. The wave spectrum fills in at higher frequencies. As the wind persists, wave height grows. Wave period increases. The peak of the spectrum shifts toward longer waves. The sea becomes more organised. Then the wind stops. Short waves decay quickly. Longer waves persist. The sea smooths. The remaining swell travels on. Now, the tide continues all the while. Perhaps it's rising, perhaps falling, but its change in depth is slow compared to wave periods. Waves ride on the tide. As tide rises, depth increases. Wave breaking zones shift. As tide falls, depth decreases. Now, beneath it, a current flows. Maybe a coastal current driven by winds or density gradients. Maybe a geostrophic current along the shelf break. Waves propagate on top of this current. Their apparent speed relative to the ground includes the current. Their wavelengths and steepness change with current direction. The tide adds another current component, oscillatory, reversing with the tide. So the nearshore environment is a superposition, wave orbital motion, wave-induced drift, tidal currents, mean currents. If you stand on the beach and watch, you see the surface expression, wave sets, water level change, foam lines moving. But beneath that, the full motion is layered. Now imagine moving offshore, away from the coast. Waves become smoother swell. Tidal range becomes less noticeable as a vertical change in a deep ocean context, but the tidal currents still exist. Currents become part of the gyre. The ocean surface might show streaks or subtle texture. Satellites can see patterns in sea surface height and temperature. Eddies swirl. Waves cross eddies. In a warm core eddy, stratification differs, affecting internal waves. In a current jet, waves can steepen. The ocean is an interacting field. Now imagine going deeper. Surface waves fade with depth, their orbital motion decays. tidal currents remain, though they may be weaker in some areas and stronger in others. Internal tides become more relevant. Internal waves propagate along density interfaces. Currents become more geostrophic, constrained by density and pressure. Deep currents flow along the seafloor contours. The ocean becomes quieter, but not still. Now imagine deep water formed at high latitudes. It sinks, it spreads, it carries a signature of its formation: temperature, salinity, oxygen. It moves slowly. It may take decades or centuries to complete a pathway. This is the ocean's long memory. It is a motion too slow to notice day to day, but it is always happening. Now, if you let your mind drift with this, you can feel the calming effect of timescales. Fast motion, slow motion, persistent motion. The ocean contains them all, and it doesn't get overwhelmed. It simply contains them. You can do the same. You can let thoughts come like waves, pass like waves, without needing to chase them. You can let slow rhythms like breath and heartbeat be your tide. You can let the deeper calm be your current. Now, let's talk about one more detail that brings waves, tides, and currents together: the boundary. The ocean has boundaries: coasts, seafloor, the air-sea interface. At boundaries, energy is exchanged and dissipated. Waves break at the coast. Tides experience friction over shelves and in estuaries. Currents interact with topography, generating eddies and internal waves. The ocean's motion is shaped by boundaries. This is why coastal regions are so dynamic. They are where multiple motions meet and dissipate energy. In the open ocean, motion can be more balanced and persistent. In the coastal ocean, motion is constantly transformed. Now, another detail that's satisfying is that all three motions can be described as waves in a broad sense. Surface waves are waves. Tides are waves. Internal tides are waves. Even some aspects of currents involve wave-like phenomena. Rossby waves, Kelvin waves. These are large-scale waves influenced by rotation and stratification. They propagate slowly. They can influence sea surface height and currents. They are part of the ocean's internal communication system. When the ocean adjusts to changes in wind forcing, it can do so through wave propagation. Signals travel, not like a message in a bottle, but like a pressure adjustment. The ocean is full of waves at different scales. So you can think of the ocean as a wave machine, a place where disturbances propagate, interact, and dissipate. Now, let's keep it gentle and choose one example: the equatorial ocean. At the equator, Coriolis is small. This changes the dynamics. Winds can drive strong zonal currents, like the equatorial undercurrent. The equatorial waveguide supports Kelvin and Rossby waves that can transmit signals across basins. During events like El Niño, changes in wind stress can generate waves that propagate and adjust the thermocline, affecting sea surface temperature. This shows how wave dynamics and currents connect to climate variability. But tonight, we won't chase El Niño into all its complexities. We will simply note that the ocean has ways of communicating changes quickly relative to its slow currents. Waves transmit adjustments, currents carry mass and heat over longer times, tides provide steady forcing and mixing. Now, another example, the Southern Ocean. Here, strong westerly winds drive the Antarctic circumpolar current, the only current that circles the globe unobstructed by continents. This current connects basins, it interacts with eddies, it influences deep water formation and upwelling. The Southern Ocean is a key part of the overturning circulation. Here, Winds and currents and waves and tides all matter. The seas can be energetic, but again, we can hold the idea gently. A ring around the world, a persistent flow. Now, let's return to the detective desk, because I like the feel of paper under fingertips. The case file has 3 dividers. Under waves, I've written pattern, dispersion, spectrum, measurement, breaking, nearshore currents, wave current interaction. Under tides, I've written tide generating potential, constituents, amphidromic systems, resonance, tidal currents, internal tides, mixing. Under currents, I've written wind-driven gyres, Ekman transport, geostrophic flow, boundary currents, eddies, upwelling, thermohaline circulation, overturning, climate. And in the margin, I've written one phrase that connects all of it: energy pathways, because that's what this case is really about, how energy moves through the sea. Now let's go back and deepen the wave story with a calm technical thread. Wave spectra are often modelled and measured in terms of frequency. The ocean surface elevation can be treated as a random process. The spectrum describes variance as a function of frequency. If you integrate the spectrum, you get the variance of surface elevation, which relates to wave height. Significant wave height is about 4 times the square root of the variance in a common convention. This is the statistical bridge between spectrum and height. The peak frequency corresponds to the dominant wave period. Directional spectra extend this, describing energy as a function of frequency and direction. Wave models solve an energy balance equation for the spectrum, including wind input, nonlinear wave-wave interactions, and dissipation. Nonlinear interactions transfer energy between frequencies, contributing to spectral evolution. In deep water, 4 wave interactions are important. In shallow water, triad interactions can matter. But we don't need to solve these equations tonight. We just need to appreciate that wave fields evolve in structured ways. Now, wave measurement is a whole world. Buoy measurements are ground truth at points. Satellites provide spatial coverage. But satellites have limitations. They sample along tracks, they can be affected by rain, they have resolution constraints. SAR can provide directional information but requires complex processing. Altimeters can give significant wave height but not full directional spectra easily. Combining measurements and models gives the best picture. Data assimilation blends them. This is how wave forecasts work. Now, wave current interactions can be incorporated in models too. Currents can Doppler shift wave frequencies. They can alter wave propagation. Waves can feed back on currents through Stokes drift and modified stress. Some coupled models include wave effects to improve current estimates. This matters for search and rescue, oil spill tracking, navigation. The ocean's surface is not just wind-driven, it is wave-mediated. Now, let's deepen tides a little. The tide-generating potential can be expanded in spherical harmonics. The dominant terms correspond to semi-diurnal and diurnal components. The equilibrium tide picture provides intuition, but the dynamical tide is shaped by the ocean's response. In the dynamical picture, tides are solutions to shallow water equations on a rotating sphere, with forcing, friction, and boundary conditions. In an ideal global ocean, tidal waves would be standing patterns. In real basins, they are more complex. Amphidromic systems arise from rotation and basin geometry. Resonance can amplify tides. Friction dissipates energy. Tidal energy dissipation is significant in shallow seas and over rough topography. This dissipated energy contributes to mixing. Internal tides carry energy away from generation sites. They can propagate and eventually break. This is a major source of internal wave energy. Now, one more tide detail. Tides are influenced by sea level. If sea level rises, the depth of coastal basins changes. This can alter resonance and friction. Tidal amplitudes can increase or decrease depending on geometry, so tides can change over decades. But the astronomical forcing remains. The ocean's response changes. This is another subtle way climate change can influence coastal processes, not only by raising the baseline water level, but by changing the dynamics of tides. Again, we can hold it gently. A system responds to changing conditions. Now, currents. Currents respond to wind, buoyancy forcing, and mixing. Wind-driven circulation is often described by Sverdrup balance in the interior and boundary currents. Geostrophic currents arise from pressure gradients associated with sea surface height and density structure. Eddies contribute to transport and mixing. The deep overturning is driven by dense water formation and upwelling. Mixing is crucial. The ocean is a balance between forcing and dissipation. Now, if you're still awake, you might notice that my voice keeps returning to the same words. Balance, structure, pathways. That's intentional. It's the way you build a calm case file. You don't throw facts, you lay them, you let them settle, you return to them. The ocean repeats itself, so can we. Now, let's take a different angle. Imagine you're a parcel of water, not a sailor watching the surface, not a scientist looking from space. A parcel of water inside the ocean. At the surface, you feel wind stress transmitted through turbulence. You feel wave orbital motion moving you in loops. You feel Stokes drift, giving you a subtle net push. You feel the tide raising and lowering the pressure above you. You feel the tide's horizontal currents moving you back and forth. You feel a mean current carrying you, slowly, along. You feel turbulence and mixing, sometimes stronger in storms. Now you sink a little into the mixed layer. Waves are less strong. Wind stress is less direct, but turbulence still reaches you. You still drift with the Ickman flow. You still feel the tide. Now you sink deeper, below the mixed layer, into stratified water. The surface's immediate influence fades, but you feel internal waves. You feel the slow heaving of density surfaces. You feel geostrophic currents moving along isopycnals. You feel the slow pressure gradient forces. You feel the ocean's large-scale circulation. Time feels different down there. Now, perhaps in the right region, you become part of a dense water mass. You sink further. You join a deep flow. You move slowly along the seafloor. You might travel for years, decades, centuries. You might eventually upwell, mix, and return to the surface. The ocean is a loop, not a perfect loop, but a set of pathways. If you let your mind become that parcel of water, you may find it easier to let go. Because you are part of motion, you don't need to resist it, you can drift. Now, another connection to life. Many organisms use currents, larvae drift, plankton drift. Fish and turtles and whales travel with currents or across them. The ocean's motion shapes ecosystems. Upwelling brings nutrients that feed plankton, that feed fish, that feed bigger animals. Currents transport heat, influencing habitats. Tides and internal waves can bring nutrients into productive zones. Waves shape coastlines where intertidal life exists. The ocean's motion is the ocean's ecology. But again, we can keep it calm. Life rides motion. Motion supports life. Now, I want to offer you a gentle case reenactment. the way a detective might walk through a scene, not to dramatise, but to understand. We'll start with a storm, because storms are a clear source of wave energy. A mid-latitude storm blows over the North Atlantic. Winds strengthen, waves grow. The sea state becomes energetic. A wave spectrum develops with energy at various frequencies. The storm moves, the wind field changes. Waves generated earlier begin to propagate away as swell. Long period swell outruns the storm. It travels across the basin. Days later, that swell reaches a distant coast. Perhaps the wind at that coast is light. The day might be calm, but the swell arrives anyway. Waves break, shaping the beach. Surfers might notice, but long before the swell arrives, the tide is still doing its thing. The tide rises and falls, and beneath it, the Gulf Stream flows, carrying warm water poleward, generating eddies. As the swell crosses the Gulf Stream, its characteristics shift. Opposing currents can steepen waves. Directional changes can occur. Now the swell reaches the continental shelf. Wave speed changes with depth. Waves refract. They align with the coast. They shoal. They break. The tide modulates the breaking zone. The nearshore currents respond. The beach changes, grain by grain. And somewhere deeper, tidal energy dissipates through internal waves, mixing the ocean's interior. The deep circulation continues, slow and steady. All of this from one storm, one event, a writing. But the ocean didn't stop at the storm. It translated it into a cascade of processes across scales. That is the ocean's skill. Now, you may notice that your mind is doing something similar. A thought arises, like a gust. It creates ripples. Then the gust passes. The ripples linger as swell. Then the slow tide of your attention continues. Then the deep current of sleep continues. You don't need to control it. You can trust the system. Now, a few more gentle technical notes, because you asked for hard science in a calm voice, and I want to honour that. In wave science, there is a distinction between phase velocity and group velocity. Phase velocity is the speed of the wave crests. Group velocity is the speed of wave energy. In deep water, group velocity is half the phase velocity. This is why wave packets move slower than individual crests. In shallow water, phase and group velocities converge. This matters for energy transport and wave forecasting. It's also a reminder that what you see on the surface is not always the speed of what matters. Energy can move differently than the visible pattern. In tide science, there is a distinction between equilibrium tide and dynamical tide. Equilibrium tide is the hypothetical static bulge. Dynamical tide is the real ocean response with wave propagation, rotation, friction, and basin geometry. Dynamical tide explains amphidromic systems, resonance, and regional variations. In current science, there is a distinction between Eulerian and Lagrangian perspectives. Eulerian is watching flow at a fixed point. Lagrangian is following a parcel or drifter. Both are useful. Waves add complexity because they cause oscillatory motion that affects what you measure. Stokes drift is a Lagrangian effect. Langmuir circulation arises from interactions, so even measurement is layered. Now, there's a phrase, the Stokes Coriolis force. In some frameworks, Stokes drift interacts with Coriolis, creating additional effects in the mean flow. The surface layer is a place where waves and rotation meet. This can influence mixing and currents. This is advanced territory, but you don't need to memorize it. You can simply enjoy the idea that the ocean's surface is a special boundary where multiple processes overlap. Now, in tides and internal waves, there is a phrase, barotropic versus baroclinic. Barotropic refers to depth uniform flow. Baroclinic refers to stratified, depth varying flow, where density surfaces tilt. The barotropic tide is the depth averaged tide. The baroclinic tide is the internal tide, the stratified response. Conversion between barotropic and baroclinic energy occurs over topography. This conversion is a key part of the ocean's internal wave energy budget. Again, a translation. Energy changes form. Now, in currents, there is a phrase, mesoscale eddies. Eddies on the order of tens to hundreds of kilometers, lasting weeks to months. They are like weather systems in the ocean. They carry heat and salt. They contribute to mixing and transport. They complicate simple conveyor belt pictures. They make the ocean rich. Now, we can drift into a calmer, more repetitive part of the script, designed to let your attention relax. We'll revisit the three motions with different metaphors, so your mind doesn't get stuck on one framing. Waves are the ocean's handwriting, sometimes hurried, like a windy day scribbling on the surface, sometimes careful, like long swell lines drawn with a steady hand. Waves are local and distant at once. They are created here and they travel from there. They arrive as sets. They fade. They break. They become foam and turbulence and sand movement. Tides are the ocean's metronome, a slow click, a predictable return. Not the same amplitude everywhere, not the same timing everywhere, but always a rhythm. Tides rise and fall. Tides run in and out. Tides generate currents. Tides generate internal waves. Tides mix. Tides keep time in basins. Currents are the ocean's long walk. Persistent motion. A drift you can map. A flow that carries heat and salt. A circulation that connects basins. A current can be fast and narrow like a river, or broad and slow like a wandering path. Currents can swirl into eddies. They can upwell. They can sink. They can carry water masses that formed far away. They can remember winters and ice and winds. Now, put them together. Waves ride on currents. Tides modulate waves. Currents feel tides through mixing. Waves influence currents through drift and turbulence. Tides influence currents through oscillatory flow and internal wave generation. It's a triangle, and inside the triangle is the ocean's steady motion. Now, I want to give you one more image to hold onto as you drift towards sleep. Imagine the ocean's surface as a sheet of glass with moving patterns projected onto it. The fastest pattern is waves, ripples of light and shadow moving quickly. A slower pattern is tide, the whole sheet gently rising and falling. A slower, still pattern is current, the whole sheet slowly sliding sideways like a conveyor belt beneath the patterns. The surface expresses all three, but none of the three is the whole story. They overlay, they superpose, they coexist. And that's what makes the ocean a restful subject, because it's motion without urgency, it's complexity without chaos, it's repetition with variety. Now, in the last part of the case file, I want to slowly close the loop by focusing on the ocean's role in climate and time, but without making it heavy. The ocean stores heat. It absorbs a large fraction of the excess heat associated with climate change. It stores carbon. Its circulation moves heat around. Changes in circulation can influence regional climate. Waves can change with storminess. Tides can change with sea level and coastal geometry. Currents can shift with wind patterns and buoyancy forcing. But these changes are often gradual. They occur over years and decades. The ocean changes slowly compared to the atmosphere. This slowness is important. It gives the system inertia. It gives it memory. It also means that understanding the ocean requires patience. You cannot observe the whole overturning in a day. You cannot see deep currents with the naked eye. You need instruments, long-time series, models. The ocean teaches patience, and patience is good for sleep. Now, take a breath in and let it out. If your mind is still active, that's okay. It can be active like the ocean is active. It can move without needing you to chase it. Let a thought come like a wave. Let it pass. Let another come. Let it pass. Return, if you like, to one simple phrase. A push, a pull, and a drift. Wind is the push. Gravity is the pull. Density and rotation are the drift. Push, pull, drift. Push, pull, drift. Now, I'll finish the case file the way I like to finish, not with a conclusion that snaps the folder shut, but with a gentle closing of the desk lamp. A summary that feels like the ocean at night, still moving, but less demanding. Waves taught us that energy can travel while water mostly dances in place. They taught us that the sea surface is a spectrum, a chord of frequencies, a statistical field that can be measured and modelled. They taught us how wind writes and how coasts receive. Tides taught us that gravity creates predictable rhythms, but geography shapes their expression. They taught us about constituents, about rotating amphidromic systems, about resonance and friction. They taught us that tides are not only a shoreline rise and fall, but a global energy source feeding internal waves and mixing. Currents taught us that wind and density and rotation create persistent flows that transport heat and salt and life. They taught us about Ekman transport and gyres, about boundary currents and eddies, about geostrophic balance and deep overturning. They taught us that the ocean is a transport system, a memory system, a slow machine. And together, waves, tides, and currents taught us the simplest, calmest truth. The ocean moves. It has always moved. It will keep moving, not randomly, not aimlessly, with rules, with rhythms, with pathways. And you can let that steadiness support you, the way a distant tide supports a shoreline, the way a deep current supports the whole ocean above it, the way swell supports a calm pattern across the surface. If you're still awake, you can rest here. If sleep is already pulling you under, you can let it. No effort required. Just the slow, steady motion of a system that knows how to find balance. Push, pull, drift. Good night.